Welcome again, dear students, to this second video of this week. I hope you people can see me. Definitely, you cannot because my video was off. Okay, so in the previous video, I explained what is one-hot encoding and how it works. Now let us see programmatically how one-hot encoding works. It will give you a better idea. It will give you even better idea. So one hot encoding, what I'm doing here, I have got same sentence, the cat sat on the mat. This is first sentence. And the second sentence is the dog ate my homework. So my objective is to create one hot encoding vectors for all the words that we have in these two sentences, right? So first I'm going to create a dictionary with the name token index. Then I say for sample in samples, these are the samples. So I take first sample, the first sample is this one. And then I say for word in the sample, right? So first it will get there, then get, then said, then on, then there, and then met, right? So to each of the token, I'm doing nothing. I just say token index at word, token index at initially there, and I'm giving it the value, which is current length of token index. Initially it is 0. So the when it takes word there, it will get value 1 because we are adding 1 into it. Next time when it comes back, token length will be 1. So we add 1 into it. So there will be 2. So when Kate comes, the token at Kate will be 2. Right. So this loop when completes for these two sentences, it will actually have a dictionary established where word, the key will be the word, and value will be the sequence where it is appearing. So it will be like this: there on 1, cat on 2, set on 3, on 4, there on 5, met on 6, and then dog on 7, because the next unique word is dog. It is not there. They have already got the 1, right? Then 8, my 10, 9, and homework 10, right? Now, once if we have created, dictionary which is representing the corresponding value for each of the word, the next is, the maximum number of words that we have got here is 10. So I say maximum length is equal to 10. So this is actually length of one vector, right? So I create here a matrix, and that matrix is having all zeros. The first dimension of that matrix is the number of samples. These are 2. So we'll be creating 2 matrices. The first matrix for this sentence and second matrix for this sentence. Now each of the matrix, it should be, n by m. The n is the length of each vector, which in this case is 10. The row, right? The maximum length is the row value. So you can see the row value, this one. Uh, it has to be 10. So you can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right. So the number of rows are 10, and the number of columns is actually the maximum value that we get, which in this case is again 10. Right. So the maximum maximum token number index value plus 1, which is actually at 10 in our case, rather 11, because we are adding 1 into it. So you can see here the number of number of columns should be 11. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the number of columns are actually token index dot values max. The max should be 9 and then plus 1. So that becomes actually 10, right? So here we actually create a structure like this. This structure is actually 2, 10 by 11, 2 and 10 by 11. Okay, now once if this is done, the next step is, initially all these are zeros. When the word is there, we would like it to be represented by the first value. I mean, because the index is 1, so we say 1 here, and everything else is 0, right? Because it is a matrix, so we are starting from 0, right?
So the first uh, the first location should be, I mean, first index, the one index should be turned to 1 because the value for there is 1. For cat, it is 2. So you can say 0, 1, 2. This is cat. Eh? The second row is actually representing cat. And then it is set. So the 3 should be 1. Eh? So you can say 0, 1, 2, 3 is 1. So the cat, set, the cat, set. Right. So you can see this first sentence is represented by this first matrix. Right. How we are doing it? We say for I sample, we are enumerating samples. Right. For J and word, we enumerate sample dot split up to maximum length. With the index equal to token index, we have already maintained the index dot get. We are passing the word. So the word initially we get there, so we get its value, right? So whatever value we get, obviously when we come here with the word there, its value is 1, right? So we say results at I, which is initially 0, and j, which is also initially 0, and index equal to 1. So we say 0 0 1 equal to 1. So 0 zeroth matrix, and in that matrix zeroth row, and first column. So we are referring to this row, this matrix, I mean uh, this matrix, and this row, the zeroth row, and this column, because index equal to, we are getting index of the word from our dictionary, and the word initially is there, so the value for that one is equal to 1, right? So we actually turn that 1, everything else remains 0. Next time when we come back here, the next word is cat. So when it is cat, the index value will be 2. So 2 is here, which we actually say in matrix 0 at row 1 at index 2, right? So matrix 0 and row 1 and index 2, which is actually this. So we say turn this 1, everything else should be 0, right? So when this loop completes, we actually have got these two matrices. This one is representing the first sentence, which is the cat sat on the mat. And this one is the second sentence, which actually you can see the first word is there is 1, so you can see 0 and 1. The second word is actually dog, right? So the value for dog is 7. So you can see here the second row, 0 1 2 3 4 5 6 and 7. So you can see the seventh element is turned 1, everything else is 0. And then the third word is 8. For 8, the value is 8, right? So you can see when we come here, 0 1 2 3 4 5 6 7 and 8, right? And then third is 8 my. For my, it is 9. So when we come here, 1 2 3 4 5 6 7 0 0 1 2 3 4 5 6 7 8 and 9. So you can see 9 is turned 1, everything else is 0, right? So this matrix is representing first sentence, and this matrix is representing second sentence, right? Now we know that these matrices can be injected, these can be sent to the neural network. That's all what we wanted, eh? You don't need to do this all laborious job manually. We have in Keras, you know, you, in Keras pre-processing text, we've got tokenizer. So same sample is here. We tokenize like this: tokenizer equal to tokenizer, number of words is equal to 5. We just want to consider top 5 words. You can consider 10 words, you can consider any number of words, right? But here we are saying that we'll consider, say for example, 10 words, right? Then we say tokenizer dot fit on text, and then we provided the sample, right? We are providing the sample, and we say consider only 10 words, and then sequence is tokenizer dot text sequence, and we are passing sample. So we get sequences here, right? And then one hot results, those results we are actually storing here, right? So if the word index will get here, and then the sequence that we have, the sequence that will be displaying, they are here. So I run this program, you can see we got 9 unique tokens here, because the is considered same word. And so when I print the word index, you can see again it is same. Again, it is same. The one that we did manually, but now it has been done. Now it has been done, through Keras. If I display the one hot encoded print, uh, print one hot results. If I do that, you can see 100 encoded results are also, though they are not as sparse as they were in our manual case, but these are still one hot encoded results, right? So usually, I mean, when in practice we are doing text processing, we will not be doing it manually the way we did here. This example was just to give you an idea how one hot encoding is working, but in practice we will be using these pre-processing capabilities of Keras, right? So you have seen in this example how one hot encoding works, right? Okay, so one hot encoding is one example of word embedding. I mean, again, just to clarify, the concept of word embedding is nothing, just to vectorize the text. When I say to vectorize the text, I mean that you want to give a number to each word which is appearing in your text. Here you can see we said, in this case, we say the should be represented by this value, huh? K8 should be represented by this value, and so on. So vectorization is nothing, just to convert words into numbers. One-hot encoding, it is binary, only zeros and one. It is sparse. When I say sparse, I mean uh, it is high dimension. Uh, you can see here each word is being represented by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 numbers. That's not a good thing. Eh? I mean, each number is being represented by 11 numbers. We are just considering 10 unique, words. But practically, if you have a text, maybe 10-page long text, it may have 10,000 unique words. In that case, it means that each word should be represented by 10,000 numbers. Not a very, wise solution. I mean, certainly it might be very easy to understand, but practically it requires a lot of memory to represent just one word. And in practice, having 100,000 unique words in a text is quite frequent. I mean, then obviously this one hot encoding is not the solution for practical world applications, right? So we need to reduce dimension for each of the word. So for that reason, I mean, there are some other word embeddings which are low dimensional. They are usually, regardless how many unique words you have in the text, they are usually 256 bytes long, or 512, or 100 1024 dimensional long, right? So we'll see in the and they are the floating point numbers. They are not binary, but they are just numbers. Say for example, with some fancy mathematics, I can say the word the should be represented by 0.15. Huh? I mean, I'm saying that I'm not telling you why 0.145, but I'm saying just one example. Maybe with some computation, I can come up with this beautiful number, and I say the should be represented by 0.14. How, what sort of computation is happening behind the scene? We'll be learning in future lectures, but for the time being, just understand that when you're talking about other word embeddings, which are not one hot encoded, they usually are floating point numbers. They are not binary numbers. The way we had in one hot encoding, there are binary numbers. And they are learned from data. I mean, that is the beauty. I mean, in data, the words have got different meaning depending on what data we are using. So say for example, I mean, just one classical example. If I say the the battery of this mobile is long, what do you think? Here, the word long, is it positive or negative? I mean, obviously, when you're talking about battery life, and if it is long, then it is positive, right? But how about if I say that this teacher
took long in sharing results with the student. What do you think? What is the meaning of long here? Is it positive or negative? Certainly negative. I mean, taking too much time in sharing result is not liked by the student. So you can see same word long in one domain it had positive meaning, in other domain it has negative meaning. It means that we should have different number representing long in mobile domain and representing long in student domain or maybe academic domain. So we say that the vector for the word should be learned from data because it will be capturing context in that domain. And when it captures context in that domain, we'll say that the understanding of text will be much better. I mean, for example, if I say, if you cross the river bank, then you will see Bank of America. Huh? See here. I mean, see this interesting sentence. I have just recalled one good example. See here. If this is the sentence, huh? If I say, if you cross this river bank, you will see Bank of America. Huh? My God. Here, the word bank and here the word bank, you can see both of these words are having different meaning. Here if you cross river bank, river bank, it is one word. Bank of America, here we are talking about the money bank, huh? So obviously word should have different embedding depending on its context. So probably we would like to have here the bank given different embedding than to this bank, right? So we'll see in our future lectures how to capture these contexts and how to learn embedding from data and how to make that embedding, narrow dimensional, low dimensional, 256, 512 or 1024, right? I mean, you might have hundreds of thousands of unique words, but when you fix dimension, then those can be limited up to 1024 dimension. 2048 is also possible, but usually these type of decisions will depend on how good you have the processing power, right? I end this lecture here. When you come back, I will be teaching you how to use word embedding and how to learn it from data and how to use pre-trained word embedding. Thank you very much.